Hello and welcome back to the channel. In this video series, we are reviewing the Salvadori's textbook Structure in Architecture. And this video is about chapter 13, and that is all about structural failures. So there were a few historical failures that I would like you to know about. So the moment humanity started erecting structures, structures began to fail. In prehistoric times, corbel dome houses of stone were built all along a band running uninterruptedly through Asia, Greece, France, and England, but only a few survive intact after 2,000 to 5,000 years. The pyramids of Egypt stand lonely among the seven wonders of the ancient world. The colossus of Rhodes, all over and over 100-foot high bronze statue to the son of god Helios vanished, and an earthquake destroyed the second longest lived, the lighthouse of Paris of Alexandria in Egypt. It was a 200 foot tall statue. Excuse me, the lighthouse. So collapses and failures plagued some of the greatest monuments of history. The dome of Saint Sophia in Constantinople began showing signs of weakness during construction, and tradition has it that it was saved by the intervention of the Emperor Justinian, who urged the architect Anthemius to complete one of its main arches that was falling, because when it rests upon itself, it will no longer need the uprights under it. That was the quote. But after two earthquakes, the eastern arch collapsed in 557, the western in 989, and the eastern for the second time in 1346. The dome was made stable only in 1847 by placing iron chains around the base. The masterpiece of Gothic architecture, the Cathedral of Saint Pierre at Beauvais in France, had the main vaults of the choir collapse in 1284, only 12 years after it was completed. And its 502-foot tower collapsed 13 days after its erection in 1573. The great domes of Renaissance, those of Santa Maria degli Angeli in Florence and St. Peter's in Rome, cracked, and few of the monuments of the past still exist to until today, but they show signs of weakness. So that was like a brief overview of the structures, and of course, many of the wooden structures burned in fires that were pretty frequent back in the day. So the main causes of structural failure, let's discuss that. This is the subchapter here. In the analysis, all structural failures are caused by human error, and that is due to the lack of knowledge or judgment. But for purposes of classification, they may be attributed to deficiencies in design, fabrication and erection, or materials. So sometimes failures are due to unexpected events, such as some natural disasters like earthquakes or hurricanes. And that is a separate category, but even these are due most of the time to our incomplete knowledge or lack of caution. Different causes often conspire and result in collapses, and technical investigations should try to explain them so that their repeated occurrence might be avoided, but should waste no time assigning blame, since this is the province of the law. So let's take a look at the next subsection, faults in structural design. So when we talk about sources, design deficiencies may occur for a number of reasons, and that is like mistakes in calculations or undetected errors in computer inputs or incomplete or mistaken interpretation of building codes. So good design can only result from experience since design is learned through many years of continued practice. So the young practitioner should not be expected to assess the relative importance of the many facets of design and should not be given responsibility for the design of essential structural components. Let's talk about computational errors. So the advent of the computer has refined structural calculations at the cost of drowning the designer in a sea of numbers. So the experienced professional aware of the common occurrence of input errors will never accept a computer result without checking it with a simplified formula or against personal experience and past records. So there is a case of Kansas City Hyatt Regency walkway collapse. You can, there is a video explaining how that happened. And please make sure that you familiarize yourself because that was a big case. And basically there was a single long hanger supporting two skywalk levels from the roof structure. And the connection basically failed. So the steel fabricator detailed, but they did not calculate the connection using two rods instead of one continuous rod. And so the lower rod being supported by a beam at the upper walkway level. So and then there was an alteration and the change caused a doubling of the load on the upper walkway support that was not detected by the structural engineers. So please read about that. There is a picture here in the textbook. I would like you to be aware of that. And we're moving to the building codes. So the building codes require required in the jurisdiction are modified every few years, and they take into account the accumulation of the new knowledge and they also clarify the meaning of their requirements. So the design professionals need to understand the codes and also different types of structures and materials. And also they need to review that with the county or authority having jurisdiction because they may vary from state to state. Most of the structural requirements in local codes are derived from or refer to a few widely accepted national codes. And the International Building Code is one of them, but there is still sufficient local code variation to demand careful scrutiny because of their legal implications. And again, that is different in each state. So please always adhere to the most stringent code. Let's talk about dynamic loads, such as wind and seismic forces. So there are requirements when there are when the buildings are designed and planned to be constructed in the areas where earthquakes are happening quite often. So the design practitioner must not only be aware of the possibility of dynamic loads, such as an earthquake, but must also keep abreast of the current literature so as to make safe and economic use of the latest information on these dangerous conditions. So, for example, in the design of the Toronto City Hall building, wind forces that were wisely determined by wind tunnel tests indicated an unexpected wind load due to the channeling of the wind through the gap between the two buildings. So the heavy steel gates of one of the first missile silos were torn off their hinges and collapsed when first used. And that was the lack of consideration on the part of the designers of the dynamic forces due to their accelerated motion. So please refer to the images here. The wind bracing system of a building must meet conditions not only of strength but also of stiffness to minimize discomfort to its occupants and avoid damage to its curtain wall. Again, there is another example, the Hancock Tower of Boston, Massachusetts. The excessive flexibility of the frame was one of the main causes of the dislodgement of a high percentage of the curtain wall glass panes and required the damping of its wind-induced motion by means of two dynamic dampers at a high cost and with too long construction delays. So the knowledge of earthquake motions and their influence on buildings can rapidly improve has rapidly improved during the last decades. Detailed maps of earthquakes intensified in the United States, and they are available. Some of them are available online. So the design professionals and architects can review them before planning anything. So with each new seismic event, more is learned about the nature of earthquakes and how buildings respond to them. Buildings are being built with a higher degree of seismic resistance, and the areas of the US thought until recently to be free of higher intensity earthquakes have proven to be subjected to them. So, for example, there was an unexpected earthquake in Virginia in 2011, and that caused structural damage to the Washington Monument and National Cathedral in Washington, D.C. Even in areas of minor earthquake activity, the codes now take seismic design into account among other considerations. And in the detailed requirements of reinforced concrete frames. Rigid structures built of brick and mortar, as well as some poorly reinforced concrete buildings and bridges, are more susceptible to earthquake damage. So, for example, California's Loma Prieta 6.9 magnitude earthquake destroyed the double-decked Cypress Street viaduct in West Oakland, and that was in 1989. A lack of sufficient confining reinforcement to prevent shear failure at the junction of the beams and columns contributed to the collapse. Please refer to the pictures here. You can see the structural damage. There's a photograph of that. And also, there was an earthquake in Chile in 2010, and the building collapsed. So the magnitude was 8.8, and that was the sixth largest earthquake ever recorded. So, and the earthquake triggered a tsunami that devastated several coastal towns. So there are images showing that. Please refer to the textbook. So let's talk about thermal movements and stress. So the same caution must be used in dealing with thermal differences, the main source of locked-in stresses. Because of their dependence on a large number of parameters, the investigation of thermal stresses is advised by most codes without specific recommendations on temperature difference or methods of analysis. As a consequence, structural failures may often be attributed to neglected thermal conditions. In a concrete dome, for one of the first nuclear reactors built in the US, the stresses due to a thermal explosion A sudden large temperature rise on the interior of the reactor, originally ignored, required a modification of the design. Also, most of the cracks in the brick masonry veneers of air-conditioned buildings, particularly in veneers of prefabricated panels, are due to the rigid connections between the exposed masonry and the interior structure that do not allow for the thermal expansions and contractions of the masonry due to daily and seasonal temperature variations of the outdoor air. Also, cracking in partitions of high-rise buildings occur when the climate produces large differences in temperature between southern and northern facades. The thermal bending of such buildings is the source of high shears in the partitions, acting as webs of vertical cantilevered beams, and of cracks due to the tensile component of these shears. Please refer to the images. You can see the building expansion thermal cracks, as well as the differential heating thermal cracks. So also there is an image showing the failure of a terminal building at Charles de Gaulle Airport in France, in Paris. So you can see that there was a unique cylindrical structure that was designed as a perforated squashed cylindrical shell of concrete with an exterior glazing, held away from the concrete by posts and tension and cables. So the tension and cables resisted the outward bulge of the concrete. Post-failure analysis indicated that there were faults in the construction that was unnoticed, that the structure had been weakening. A sharp temperature drop occurred one morning that caused rapid contraction of the tensile cables. So this in turn caused the posts to put additional pressure on the concrete as the cables contracted. The shell was designed for these pressures. However, at one location, a ramp penetrated the shell, thus creating a discontinuity. This imbalance of forces on the shell, in addition to construction flaws, led to its complete collapse in this area. So, we see that unbalanced forces due to thermal differential significantly contribute to the collapse of Terminal 2E at Charles de Gaulle Airport in Paris in 2004. And that happened just 11 months after its inauguration. So we can see that the damages can happen right after the building is constructed, or a few years, or a few decades, or even centuries later. Let's talk about foundations. The mechanics of soils has become a reputable field of science through the investigations of the last 100 years. It is one of the most sensitive facets of foundation design. No structural engineer will assume the responsibility of such design without a soil investigation performed by specialized labs that specify the bearing capacity of the soil, the maximum differential settlements to be expected, and the type of foundation most appropriate for a chosen location. Settlement differentials are of particular interest to the designer since they may cause large cracks in curtain walls and partitions and weaken the structure. A substantial number of failures in slabs on grade and curtain walls are due to foundation deficiencies related to changes in underground water levels and new construction. So, for example, the National Theater in Mexico City, founded on a soil consisting of a mixture of sand and water, subside many feet at first when its weight squeezed the water out of the sand, but then was pushed integrally upward when a number of high-rise buildings were erected around it. In this case, the evenness of the displacement and the monolithic reinforced concrete structure prevented damage to the building. And Here's the image showing the settlement cracks in curtain wall or partition. And also you can see the foundation failure that happened in China when rain-soaked soil was excavated beside the pilings of a multi-story apartment structure. So the combination of removing soil that was holding back lateral pressure from the building foundation, plus additional lateral pressure from the excavated soil piled on top of earth behind the building led to the collapse. With the extra load on earth that was already weakened from rain saturation, lateral displacement caused the entire building to slide forward and snap the foundation pilings, then collapsing entirely into the excavated area. So please take a look at that. Let's talk about structural redundancy. So some of the most spectacular failures take place in structures lacking redundancy. Statistical indeterminacy is necessary but not a sufficient condition of redundancy. For example, if a uniformly loaded fixed beam were to fail at one of its support sections, indeterminacy might theoretically allow it to carry the load as a cantilever. But if it was originally designed to resist the largest bending moments in a fixed beam, which usually occur at its ends, the stresses at the cantilever support would increase by a factor of 6 and collapse the beam. If the midspan section of the same beam failed and it carried the load as two cantilevers half its length, the stresses at the support of these cantilevers would be 50% above the maximum original stresses and dangerously near collapse, since on average, safety factors take into consideration a load increase of the order of 67%. Redundancy requires providing additional structural resistance in case of failure, particularly when the loads on a structure are supported by a large number of identical elements, as in space frames, for example. So the roof of the Kansas City arena in Missouri was hung by means of 48 steel hangers from 3 external pipe frames. And one of the hanger connections failed during the exceptional rainstorm. The load supported by that hanger was transferred to adjoining ones that should have been able to carry the additional load. Since they were unable to do so, a chain reaction developed that collapsed a large section of the roof. Luckily, without loss of life, because the arena was unoccupied at that time. So please take a look at the images. You can see fixed beam, then the full cantilever and half cantilever, how the redundancy is shown in these beams. Also take a look at the at another image, and you can see there's actually that hanging roof of Kansas City Arena. There is a section showing how actually that happened. You can see the roof structure, and you can see the internal support members here as well. So a chain is only as strong as its weakest link. So the load hanging from a chain is channeled from its support along a single line as a tension member. In the case of hanging weight, this single load path, or SLP, is a straight line. If a link fails, the weight falls. A chain hanging from 2 supports may support a distributed load along a curved line. The curved chain is also an SLP structure. So modern suspension bridges are supported by multi-stand cables. This strands sharing the load in this case as a multiple load path or MLP or redundant structure. If some strands fail, their share of the load is redistributed to other strands. As a consequence, the structure survives until all strands are broken. A simple frame consisting of 4 bars form an unstable parallelogram and moves under the application of a load. With the addition of a diagonal bar, the truss is stabilized and becomes an SLP. The loads are channeled from one support along the bars to the other support. Should any one of the bars fail, the truss becomes unstable or will collapse. And again, MLP is multiple load path and SLP is a single load path. So here you can see the images, you can see the truss determinacy with and without the lateral bracing. While most trusses are usually built as MLP or redundant structures, the stiffening truss um, can carry the roadway and it can be an SLP structure. So in the worst of all combinations, when the supporting SLP I-bar chain fails, the SLP roadway truss collapses as well. So let's move to the next subsection, that's buckling and redundancy. Redundancy is particularly needed when a chain reaction may be started by buckling. It was noted that buckling is a sudden phenomenon that occurs without warning and is usually followed by failure. The particular case of buckling involves torsion called lateral buckling, prevents the same dangerous characteristics. And please take a look at the images here. You can see the space frame failure at Hartford Civic Center that was in Hartford, Connecticut. So also there is another example that was a reticulated dome of flight pipe bars over 300 feet in diameter, and that collapsed in Bucharest in Romania in 1960 under an exceptional snowfall. So that was unexpected and that was not calculated for. Connections. So the states of stress in the connections of structural elements are particularly complex. It will become as no surprise to the engineer that they are often the source of failures. Codes and manuals give criteria for the design of connections based not only on refined mathematical stress analysis, but also on series of tests on models or full-size connections. So because of their complexities, failures of connections occur more frequently than those of structural members. Connections are designed with high coefficients of safety. This is particularly true of space frames whose connectors may have complex shapes and stress distributions. Let's talk about unexpected loads. So those are usually natural or human-made phenomena, and such disasters as hurricanes, snowstorms, tsunamis, and fires or explosions are actually, they belong to this category. These do indeed bring havoc to all kinds of small and large structures, but only when the structures were not designed to resist them, then forces reach new heights, or it's called a common occurrence, or when engineers forgot the lessons of the past. So, for example, the collapse of the Tacoma Narrows Bridge in Washington State in 1940 was identical with that of the Wheeling suspension bridge over the Ohio River in 1854. At that time, that was the world's longest suspension bridge. But the memory of this disaster, vividly described in the local press, had vanished. In these cases, wind-induced aerodynamic oscillations of gradually increasing amplitudes caused the collapse. In the case of the Tacoma Narrows Bridge, the great flexibility of the structure and the lack of appropriate wind bracing contributed to the failure. So let's talk about ponding. In more recent collapses of large structures, the load due to natural forces did not reach the design values recommended by the codes and must be attributed to faulty design. For example, the collapse of large flat roofs subjected to rainstorms is often due to a chain reaction phenomenon called ponding. The flat roof caves under the weight of the rain, acquiring a concave shape that does not allow the water to reach the level of the drains. The increasing weight of rain accelerates the caving of the roof, which is transformed into a pond containing an increasing load of water that eventually may collapse. Appropriate roof slope to promote runoff and appropriate distribution of drains at correct levels prevent ponding. Flat roof buildings are also typically designed with overflow scuppers at their roof perimeter as another safeguard against ponding. Let's take a look at other causes of failure. So the human-made causes of failure, such as fires and explosions, can be as damaging as those due to natural phenomena. So, for example, a high-rise industrial building in New York City had two of its facades blown out from top to bottom by a bizarre sequence of events attributable to human error. So, a cylindrical steel compressed air tank exploded in the middle of the night, probably due to a deficiency in the tank or the malfunction of a pressure release valve. The tank's explosion shot up its dome top against an overhead gas pipe that sprang a leak under the impact. The gas would have been confined to the floor where the tank was located, where it um, not for the alternate motion of the elevators in the building that sucked the gas up to the high floors and pushed it down to the low floors in a pumping action. And that spreaded gas throughout the building. So please take a look at the images to see how that happened. So let's move to the faults in coordination and supervision. So a construction team of a large modern structure consists of a large number of specialists. And let's name all of them. So it can be the architect in charge or the architect of record and his or her team with the design professionals. And there's a project architect, landscape architect, interior designers. Then there's a structural engineer and the team, the mechanical engineer and team, electrical engineer and their team, plumbing engineer and their team, the soils engineer, the environmental designer, or lead consultant, or any type of sustainable green building consultant. Then the contractor and team of specialty subcontractors, then the owner's reps, and a variety of other experts on curtain walls, roofing, costing, scheduling, materials, and so on, you name it. So the communication is one of the most frequent failures when such a large team is trying to work on one project. So the smooth coordination between all the facets of construction requires cooperative communication between all the members of the team and implies a knowledge of the basic requirements of the other trades on the part of the representatives of each trade. So the architect needs to know how structure works. They need to know the basics and has the fundamental knowledge of the electrical, mechanical, and plumbing systems, as well as other building systems. So in spite of the interest and goodwill of the members of the team, unavoidable conflicts will arise during construction, and clarifications or change orders will be issued. It's totally okay to have change orders, but some of the teams are so afraid of them. But that's part of the project life. Besides that, any tendency on the part of the contractor to cut corners in order to maintain the schedule or enhance profit, involuntary human error may be responsible for such mistakes. So, in this context, it suffices to mention the consequences of the misplacement of the reinforcement in concrete structures, the deviation from a prescribed sequence of operations in welding, for example, in steel connections, the tightening of connections that should allow thermal movements, or the improper curing of poured concrete. So those were just a few examples. So the architect and the engineering team must realize that there is a wide gap between a theoretical conception and its execution in the field, and that the job of the contractor may appear less creative than theirs, but it's certainly as complex and demanding. So a harmonious collaboration between the legislative and executive branches of the construction team is a necessity if failures are to be avoided. So let's move to the faults in materials. So that is an important part too. And the most essential properties of structural steel are strength and ductility. So, and let's talk about that a little bit. So these properties depend on the chemical composition, the thermal treatment, and the rolling of steel shapes during manufacture, and should be checked of each batch of steel used by obtaining and corresponding data from the manufacturer. So this is something to remember, and no operation involves greater risk in steel construction than the welding of connections. So the welding materials, the type of flame, the temperature, and the speed used in this operation influence dramatically the strength of the connections. Concrete. So concrete properties depend on its composition, and that is the ratio of cement, sandstone, and water used in the mixture. Besides the type of cement and the strength of the stone, also we need to establish the granulometry of sand and stone, and that's the size distribution, to guarantee that the voids between stones are filled by the sand grains and those between the sand grains are filled by the cement. So that is something that we always need to check, and there are a few tests available, so we already spoke about them. Let's move to the new materials and methods of load estimation. So the advent of new artificial materials such as plastics, glass fiber, and carbon reinforced composites are finding increased usage in buildings as well as in aircraft structures. So the designer is required to have a thorough knowledge of their properties and methods of construction. And all those new building materials must be tested and carefully monitored by the methods of QA, QC. So for instance, a strength value, one standard deviation, or STD below the mean indicates that about 84% of materials will exceed this value. For two STDs, about 98% will be greater. Strength and pressure or stress frequencies may be plotted on the same type, and infrequent high stresses may overlap infrequent low strength values. The size of the overlapping region is indicative of the probability of failure. The size of this area may be reduced by reducing stresses, using larger numbers or increasing strength, or using better materials. So the ratio of mean strength to mean stress is the mean safety factor. uh, Fatigue failures. Another important mechanical action that can result in structural failure is metal fatigue. It is common experience then to break a piece of wire. It has to be bent back and forth repeatedly. The material is being weakened by fatigue and eventually fails. So structural components that are subjected to repeated loading, usually from loads such as wind, snow, thermal stresses, vibrating machinery, and earthquakes. So those cyclic loads are usually in the elastic range and do not result in large deformations. Nevertheless, because of their cyclic nature, they produce fatigue. Structures can withstand hundreds of millions of cycles without failure, but a sudden, unexpected high load may produce fracture. In the case of highway bridges, it is often the design for fatigue resistance that becomes the controlling criterion, not simply stress. So please take a look at the image here. You can see the Aloha Airlines Flight 234 fuselage failure. And that fatigue cracking leading to a sudden failure along a series of rivet holes in the backward section of the plane caused the fuselage to rip open in midair. Although the flight attendant was killed, remarkably, the plane was still able to land safely with all passengers. Also, corrosion caused by water, acid rain, and other atmospheric conditions roughen unprotected metal surfaces and also cause pock marks that can create stress concentrations. Combined with repeated loading, the component may be subjected to stress corrosion fatigue. And let's move to the last subsection, and that is the consequences of structural failures. So we all know that structural failures may result in bodily injury and loss of life. And they're always the cause of financial losses, damaged professional standing, and even more dire consequences for one or more members of the construction team. Unless amicably settled among the parties involved, major collapses as well as minor failures lead to litigation through the courts or arbitration proceedings. And since the architect's technical consultants are often his subcontractors, the architect becomes legally and financially involved in litigation. The architect is then compelled to sue his consultants and the contractor in turn to sue the entire architectural team. The owner, who certainly has no responsibility for the failure, is usually the originator of these complex, prolonged, and costly maneuvers in which each party is supported by a group of experts. It's not unusual for these legal proceedings to last long periods of time, sometimes years, and for the request of damages to reach large amounts of money, even when punitive damages attributable to bad faith or fraud are not involved. In few human endeavors is an ounce of prevention worth so many pounds of cure. So, when we talk about the remedy for the occurrence of structural failures, if there is one, so what we need to keep in mind is the professional development. And also there are institutions that offer the courses where, for example, engineering companies and offices may offer those courses and require their engineers to attend those courses given at universities, as well as those provided by professional societies at conferences across the US and internationally. So people need to constantly educate themselves in order to prevent the failures, especially when the new building materials are specified. Um, so that was it. So since the structures and the architecture in general is in charge of health, safety, and welfare of the general public, this is why it is important to learn about structural failures. And this wraps up our chapter 13. Thank you so much for watching. I will see you in chapter 14.